I have these things that, and then I will say this polymer, polyethylene, right? Polyethylene has a melting temperature, right? And then you have a thermal. So thermal property is very important for us to know. So I guess you care about thermal property. And how people measure those thermal properties such as a TG, TM, and also what is known as degradation temperature. This is one of the things that polymer, if you make the polymers and you put it into an instrument that can heat up the sample, not just 100 or 200 degrees C, it can go up to 1000 degrees C, see when the polymer sample thermally degrade, burns. Okay. Or in other words, burns, right? This is an organic polymers typically, so unless you have inorganic polymers, that has a different story. A typical organic polymer has a degradation temperature. So thermal property, probably what you want to know, one thing. What kind of other property do you think that is you want to know about this? Density, hydrophobicity, how flexible the polymer is, the physical strength. All right, so so the one that I want to go after is actually mechanical properties. And or some things are flexible, or hard, stiff, tough. I'm just kind of putting this all kinds of different one. And then this mechanical property should be, we also need to know. And there's a section later in the class, I kind of introduced different kinds of ways of how people measure the mechanical properties. And then mainly what is called the stress strain curve. It is a very common, this section is very kind of closer to what has been learned, what we have learned from the studying the metals in the past. That's a metallurgy and the metal properties, ceramics, and these are the material science. Polymer has a lot of strong ties to the material science in its academic study platforms. And somebody says molecular weight. Okay. And I will say the molecular weight, I want to say molecular, you're going to say, instead of saying molecular weight, I want you to say, we are talking about molecular weight distribution. Okay? So it is, if for example, if I just graphically draw it to you, this is your molecular weight. And then this is, I guess, a weight fraction of dimer. So this is, I guess, a number of moles. So this is an I. And then more typical polymer has this kind of distribution, molecular weight distribution. So think about some polymer has a narrow molecular weight distribution, very narrow. Some polymer has a very broad molecular weight distribution. They do not have the same physical property, mechanical property, even thermal property cannot be the same. So molecular weight distribution is something that we need to know. And we are talking about number average, weight average, and what is called the MW over MN, and this is called the dispersity, polydispersity, and this is the measure of how broad the molecular weight distribution is. And let's see, density. That is good. Viscosity. There we go. This is I like so those who are asking this viscosity, I would like to highlight it. Okay, so viscosity is, I put emphasis on the understanding the viscosity because the why people see that polymers is a useful material is because it's a processability. Polymers are easier to process compared to the metals and the ceramics. So therefore, the understanding the viscosity is a very important, because you want to easily kind of make this polymer softened up and pushing through the nozzles and then extrude them out, make a fiber spin, or also you want to make the injection molding to make a lot of parts. So the processability is actually the part that I was not able to cover most of the case, although it's very important in this portion of the class. But I can certainly talk about the viscosity itself. This is something that I want to update in my class content in the future, adding a little bit about what kind of different types of processing polymers people has done in the past. Okay. Density, hydrophobicity, hydrophilicity. Yeah, so that's also another one. But let me kind of asking you a question on this. Continue to do this. This polyethylene that you see here, right? But you have heard about high density polyethylene, low density polyethylene, linear low density polyethylene. The list goes on and on. Even these two are separate recycling code that we have, right? Do you know how they are different? Their densities are different, certainly for sure, but from the molecular sense. Anyone? We talked about this. The high density polyethylene is polymer chain looks like this. So it is a CH2 this forever. Okay, so there's thousand is actually not enough. You have about, let's say, 10,000 repeating units of those. The low density polyethylene in contrast, they have a chain, but there's a branching. Okay, and that branching has a branching, and that branching has a branching. So branches on a branches. So this is a chain looks like chemically identical, but the high density is a linear chain architecture. This is a branched. Okay, so this is a branched chain. So another concept that will be also useful to know is we call the chain architecture. Architecture. Also, we can just simply say as a branching, because from the experience, high density, low density, as a physical outcome is a difference in density, but real molecular differences, their chain architecture differences, whether it's a branched or not. In some people in the research is actually they want to make a ring polymers, how the ring polymers are different from the linear polymers and so on. So that's something that will be related to. Okay, and this chain architecture branching is actually related to, once again, the processability, how easy to process this and so on, and then the chain architecture is one other things. Okay, so far so good. Okay, branching, yeah. And then I want you to think about one other things that has been covered in your class, which is copolymer. Was it covered in your class? Right, the random copolymerization was covered in your class, and the reason is not only just making polymer using two different monomer unit. Not just because of that, we want to actually make the polymer in the industry scale so that they can have something more better property without in a way without making new kinds of monomer as an example. So one a very famous example is this. This is a polystyrene, right? And then this is a what they call the acrylonitrile. Okay, so it's called a PAN, and this is a PS. Polystyrene we are using as it is, making styrofoam cups and sometimes a clear plastic covering because it's very cheap monomers that we can easily make, and and then that's became one of the mainstream polymers. This PAN is the polymer coming from acrylonitrile, CH2 double bond CH with this. It is one of the kind of odd monomers. It is expensive monomers. And not only that, it is very difficult to process these monomers into, once you make the polymers, this is a very difficult to process it. So what happened was that this is, one has a very nice, desirable chemical resistance, although it's very difficult to process at 100%. But if you make this one into what is called as a random copolymer, so instead of making this random copolymers, people are using this notation very likely instead of using the square bracket, they are using this normal simple bracket, and then they say these are the repeating with, let's say, molar composition is X and 1 minus X or something, so that they have a random copolymer. And this one itself has a random copolymer co-PAN, and that we call the SAN copolymer. This is an industrially produced polymers to have a, in a way, better property than the polystyrene itself. But we do not want to reinvent new kinds of structures. So they make this sand copolymers. And on top, actually, has anyone heard about ABS? ABS plastics?
It's used in 3D printing.
That's right. Not only that, before 3D printing is even like 3D printing, have you heard about Lego? Right? The Lego block, that is made out of the ABS. It is a very nice polymer. And the ABS is, A is, that's right, A and the S. I don't, somehow they got this name coming from, but ABS is coming from this acrylonitrile and styrene copolymers are being grafted onto the rubber, which is a butadiene. So it is a butadiene grafted by styrene acrylonitrile copolymers. And instead of using the, there is a one called high impact polystyrene, which is in a way, I can say that that's like butadiene with a styrene graft. Okay, and this one is a butadiene polymer with acrylonitrile SAN. So what it looks like in the molecular sense, you have a butadiene and this one is grafted. Okay? Polystyrenes are grafted on polybutadiene. Polybutadiene is one of the rubbers, right? See, it looks like this. And there is a very flexible polymers, one of the main source of the rubber. So the rubber typically made into small kinds of particles, and then they actually put the styrene, and then they are being grafted here. Whereas the ABS is more like this one with a lot of SAN, styrene acrylonitrile. And the reason that Lego is actually, if you look at the actual Lego, it's pretty tough. It's pretty good. It has a pretty much good mechanical property compared to the polystyrene because of the not only it has a butadiene, making me more soft but impact absorbing material, but also the acrylonitrile making more chemically resistant. So it is a lot of engineering has been went into a play, and this is also acrylonitrile group making more easy to be colored. I just keep this one in my mind that I just have to say this because this one just keep on bothering me. So this one is one of the thing that, do you know chemically why people call this one? This is a cyanide, right? So, so you can say that this is a polycyanide, and that doesn't sound great, right? If you want to sell the product that cyanide is a poison, so they don't want to sell it. So they actually come up with a name called acrylonitrile, and so that people, general public do not know it has the same chemical structure that is a cyanide, which is a poison. Anyway, why am I saying about the copolymer is this is one of the things that I want to say, copolymer, or it's just essentially you have a A, you have a B. You want to combine those properties together. Okay. If you want to combine those two properties, somehow you can hopefully you can have a property in between those two. And the one way is you use a monomer stage, making it to a random copolymer. That's one strategy, and sometimes working, sometimes doesn't work. I cannot imagine making random copolymer of a styrene with something like nylon. That doesn't work. Nylon has a very different chemistry with a styrene. So, some chemistry are compatible for making a random copolymer. Some chemistry you cannot do. So then what people usually think about as we learn from the metal, we just simply making what they call alloy. You mix them together and make a polymer blend. So that's one way is making a copolymer or making a polymer blend. You mix those two polymers. Unfortunately, it doesn't work that easily. Okay, if the polymer blend is just like works like a charm, then we don't have to worry about making different grade of polymers. And probably polymer scientists will run out of their business because it's so easy to tune the material property by mixing those polymer A that is hard and polymer B that is a soft, and then you mix them together to kind of dilute in the property. But that doesn't work that way because polymer A and B are easily immiscible. They are not. It's like oil and water. It looks like a chemical structure is the same. One good example is actually, you see the high density and low density polyethylene, they are not miscible. You put that in, they will phase separate into two separate domains. So, chemically it looks the same, only difference is their branching degrees. And if the branching degrees are so different and they have its own domains of two different melting temperatures, and optically they look very different. So polymer miscibility, polymer blend is something that I also talked about in my recorded lectures that we can talk about your questions after you look at these problems. And then there's another question, something called A block B. So you make A and you make a B. So you make it into the chain. So let me put in a different color. It's a traditional block of polymers. So you make blue chain and the red chain, making a block of polymer. And then this block of polymer can, although the A and B would like to phase separate, but they are tied together the chain. So it does not form this big, large segregated domains, but they what we call the self-assemble into a very nanoscale structures. And these are the all polymers. There are examples, actually, polymer blends are being commercially used in millions of tons a year are being used, and there are black copolymers are being used in the industry, millions tons a year, hundreds of million tons a year. So I mean, bulk scale production is possible, and the copolymers, polymer blend, the black copolymer, but it has its own system that has been successful. It's not all the system that is always being successful. So this first thing effort is understanding that we have a polymer that can have a different thermal properties. And the second one is now you know the option that, yeah, we can make the polymer into a even more than what they call is a copolymer, is a chemically heterogeneous mixtures, and how you're going to control the structures of this copolymer is another big theme in the polymer material design. Why people are putting so much emphasis on copolymers not in the class, in the industry, is because you don't want to invent a new wheel. Okay? Another viable option for you is come up with a new monomers, means new chemistry, new monomer chemistry, making a new monomers into a larger scale structures, productions, and then develop its own processing technique. And those are the very kind of big problem to deal with. So to kind of go around the problem is, okay, we know how to handle A polymer, we know how to handle the B polymers, making a larger scale. How about combining those two to see if we can kind of solve the problem to have the property that we need. Okay, these days we are facing a different problem because of the polymers are so well made. We want to even now degrade the polymers and recycle the polymers, and this is one of the big things that people are think about solving the problem these days. Okay, so I want to talk to you about the polymer as a material, new materials. And here is a diagram of what people used to think that as a materials. Okay, and there are two materials historically in the material. Okay. One is metal, the other is ceramics. I mean, if you go to the really old days, there's only one material, that's a ceramics. Right? These are the ages, I don't know, 5,000 years ago, we don't even know there is a metal, so we only use a stone to kill the animals and I guess the people to survive. But now the eras of metal came in as a material, and the material diversity really boost up our civilization to go. And then the polymers, this is a before 1950s. Is actually during the World War II is one of the big boost in the I think the 1950s is a little bit too hard, so I would say 1940s. Okay, so people start to know that there is a kind of viscous gummy material as a product that is a failed organic synthesis. That's what my organic synthesis friend is saying that, oh, I have a polymer at the bottom, so my reaction is failed. So they have to try again and again to make something that is valuable. But now the polymer becomes a very useful material, and then becomes now one of the new materials. I mean, the metals are still very important. Ceramics, we know is all important. And the ceramics, silicon, computers, right? Information ages, so there is no doubt that is important. But now the polymers, plastics are important. And people, this one has its own kind of the area that used to be the people used to have a cup, right? People used to have all kinds of the household that used to be made by the metals and the ceramics, all replace it. I mean, the cup is a very good example. We are polymers are being replacing those area. And then this is because of the polymer has the pros and cons. So let's talk about why polymers are being accepted and we are using it 2000s. So this is no doubt that polymers are an important part of our daily lives. You guys can imagine the life without polymers from when you wake up in the morning until you go to bed. We just has so much dependence. We just want to be a little bit more responsible using these polymers, but polymers are very good. And why people like polymer as a new material for the modern society. So let's talk about the pros. So how, as a, I guess, a new material, I guess I'm talking about properties, right? So what's good thing about polymer over metals? Anyone can put anything in the chatting box, or you can say anything. I mean, it does have a better, quote unquote, better property than metals and ceramics. That's why people use polymers, right? So is there anything that you kind of heard of? Corrosion, okay. But somebody said corrosion, but the corrosion itself can be, I mean, metal people was pretty working hard yet. I mean, it still has a corrosion issues. It has but they can make it a different alloys to make the corrosion, to handle the corrosion. But less corrosion, yeah, that is good. I can give you that. Any others? Yes, somebody say lighter, right? Lighter material. This is a very big, okay? Lighter, less dense. And the new airplane, I think it's a Boeing 797 or Dreamliner, and that's the one that is being the material is a lighter, so that lighter airplane consume less fuels, so more economic. And then that's what this whole airplane from the new Boeing was made out of the composite, epoxy composite. The whole thing is a one molecule actually. And then they put the engines in, and so it has a comparable mechanical properties. It could have been engineered to have a comparable mechanical property to metals. It can be much lighter. Somebody say more. Somebody say cheaper. Yeah. Okay. Cheaper. Yep. Cheaper can be also true, and the reason is because of. But I think that it can be cheaper too, right? The metals can be cheaper as well, but certainly the lighter is the big portion. And somebody say more flexible. That's also actually important. Flexible. One of the things that polymers are uniquely have as a material is you have a rubber band, right? Rubber band is really the one of the unique one. If you stretch the rubber band, you can stretch 200, 300. Can you imagine doing that with ceramics? Or no way, right? It's very fragile. And also, what about metal? Metal is not flexible. So the flexible rubber band is a tire. I have actually one class video, class slide that I made it before. During the World War II, there was a shortage of the natural rubber. And because of without rubber, the country, the United States cannot be functional, because you cannot drive the car, you cannot fly the airplane, right? So there's a big campaign that do not drive around too much. It's not because there's a shortage of the fuel, there's a shortage of the actual rubber supplies. And then a lot of synthetic rubbers are being produced. And that is actually what we use in some of the ways. You guys about neoprene. Neoprene rubber is a neo means a new rubber. And that was invented by one of the famous scientists named Crothers, okay, who's an inventor of the nylon, by the way. Easier to produce. There you go. Who said that? Easier to William. Wow. Who's William? Williams Glasso? Grasso. William. That's a good answer. Easier to process. This is actually to me there are two answers that I was looking for. Is material properties that pretty much many people know there's a lighter material, but easier to process, and that makes essentially the most important properties is a mass production. So that's why this mass production, it can be made it into a cheaper ways to make massive amount of material. Certainly the original monomers prices is not so expensive, but remember that when the nylon first came out as a nylon stocking, it is more expensive than the silk stocking because people love it. It lasts, it's very, very strong and lasts for a long time. And yep, is an insulator, not conductive. As metal. That is true. So that's why we are using the polymer as insulating wires to kind of to insulate this the metals. But you know, this always a new opportunity comes out. There's something called a conductive polymer. This is also one you to think about as a new ideas. Conductive polymers is possible. It was a kind of a curiosity. Okay, so people know that it's a thermally, not the thermally, but it's actually thermally also very insulating, but electrically not is an insulating material, but you can make electrically conductive or semi-conductive polymers, and which is easier to process and which is also bendable, right? You know, everything together comes to one word: flexible electronics. Right? So there are people pushing this idea to the making these polymers to be easy to be used. You can dissolve it in, and you can put it into the more electronic components, and then they want to make the LED polymers. There's a flexible conductors, and you can use that one for. But you know, if you're actually looking at the foldable phone that you recently probably saw in the new products, this is actually not using flexible polymer, flexible conducting polymers, but they're just simply using the silicon that is actually conductive. When you have a silicon, it's very amazing that the property of material, we all know that silicon is very brittle. Ceramics are very brittle. But if you make it thinner and thinner and thinner, it can be made it into a very flexible. So that they're using that kind of a dimension dependency of the overall mechanical property and to make this one as well. So I think that but you know, I kind of find out is the usual two or three one that I've been want to emphasize this, but there's a bad thing about polymers, right? Not as good as the metals. What is not as good as metal? I mean, this is all good, so you should replace the metals, but there is a place that we cannot use plastics because of, anyone? Quick guess? Because in the kitchen, right? If you go to the kitchen, there is always metals in the kitchen. That's right. Somebody said temperature, right? Temperature. So eventually it will melt, but I argue that, I mean, to me, the thermal degradation is a main problem of the polymer as a material. Because we cannot use this one for high temperature applications, but there is what is called the inorganic polymer. To be made into the ceramic precursors. And the people studying on inorganic polymers such as the silicon base and other kinds of polymers, and they are using this to make this high temperature application, and which has an application in NASA and aerospace and defense. A lot of, like, the area that they don't care about the, he said the performance is the most important criteria for their material selections. And so there's a lot of opportunities, actually. People are still looking into new problems. But remember that this is the most significant problem that you want to remember that when it comes down to. And maybe it's hard to dispose of plastic because it's harmful to the environment. That is also recycle. How to recycle the polymer is a really big problem. It ties into what I said before, A and B not miscible. As we learn from there's a whole thermodynamics we understand now. Large molecule mixture is very different from small molecule mixtures. Waters and ethanol is easily to be mixed, right? But if you have a water version of, let's say, polyvinyl alcohol, and then there is another one. Yeah, I mean, for example, like I said, polyethylene, high density, low density, they are not miscible. Polypropylene, polyethylene, there's only methyl branch difference. I mean, it should be not that hard, right? They super hate each other. They don't miscible at all, right? So think about not just the hydrophobicity, hydrophilicity, even what seems like all hydrocarbon-based polymers, they are not miscible, and people trying to cycling it. There's a lot of idea now. How can we actually, instead of recycle, means you are kind of using it again or a kind of similar one, but how you can actually chemically convert it into the different kinds of it's called the upcycle, is what I have in mind, and I'm trying to find, many people trying to find the solution of kind of producing a value-added product by degrading the polymers and using as a polymer as a feedstock for making new chemicals. This is just at the initial stage. I don't think it has any big